Hello, in this video we are going to look at curl and divergence. Curl and divergence are operations that are applied to vector fields. So we're going to start off by looking at the curl. And given vector field F equals Pi plus Qj plus Rk, the curl of F equals Ijk. So the determinant of the 3x3 matrix Ijk, we've got partial with respect to x, partial with respect to y, partial with respect to z for the second line here, the second row. And then we've got our vector field PQR for the bottom row. And if we go through and calculate the determinant where we're going to apply this as an operation onto R, we'll have the partial of R with respect to y minus the partial of Q with respect to z, then minus J, partial of R with respect to X, minus the partial of P with respect to Z, plus K, and partial of Q with respect to X, minus the partial of P with respect to Y. Okay. And so that calculation will produce the curl. Another way of going through and writing it, if you're looking at this and saying, you know what, this looks kind of like the cross product, except we've got these partials here in the second row instead, that is correct. If you go through and calculate the gradient vector crossed with the vector field, that also produces the curl, right? So if you go through and look at this, the gradient, if you think of the gradient as a vector, then it's the partial with respect to xi plus the partial with respect to yj plus the partial with respect to zk. And then if you cross it with the vector field F, which is Pi plus Qj plus Rk, then it does produce the curl, right? These are going to be the same. Okay, so that is the curl. What is this? Like this ending, this result that you end up getting, what is that? The curl is the vector around which rotation at a point happens in the vector space. Sorry, in the vector field. Also, the length of the vector tells you the strength of the rotation. So the length of the curl vector So the idea is that if you've got a vector field, in the vector field, of course, there are vectors pointing all different directions. If there is a rotational aspect to the vector field, so if you look at one particular part of the vector field at a point, and then around which there happens to be this type of behavior where you have this kind of rotational behavior, then that's going to produce a curl vector that is perpendicular to that rotation. Right. So the curl is the vector around which the rotation happens. All right. So around which the rotation occurs. Okay. So here's your vector field behavior, and then here's your curl vector, and it is the curl vector. It's the vector field. The rotation is around the curl vector. So the curl vector is perpendicular to the rotation. So a good question is why? If you look at this, you look at the result that we got here, the vector that we ended up producing by going through and doing the determinant calculation. What does that have to do with ending up producing a vector that is, perpendicular to the vector field behavior? I'm certain there's a lot of different ways to go through and show this. The way that I go and show that that the y here ends up producing this vector is by actually looking at the calculation. There's probably a way to do it by actually digging into the cross product aspect of it, because cross products, of course, produce vectors that are perpendicular. But that's not something that I've ever dug into. But what you can do that's really simple, if you actually just think about it, is, why does the curl produce the vector around which there's rotation, is to actually dig into the individual components. So for example, if you look at the z component, if you look at the z component in the curl, it's this guy here, right? So we get the partial of p with respect to x minus the partial of q with respect to x minus the partial of p with respect to y. All right, so what we would expect is that this quantity, right, should be large when there is rotation in the xy plane, right? So the z component is going to be the z part of the vector from the curl is going to be the part that is perpendicular to the xy plane. So we should expect that when this quantity is large, when the z component is large, that's when we should see rotation in the xy plane. All right, so we could say that this should be large when there's rotation in the xy plane. And vice versa. When there's rotation in the xy plane, we should get this, should end up being a large quantity. All right, so we can go through and think about what what type of behavior we would get that would represent this quantity. So the way that we can do that is we can go through and we can say, if we go back to the vector field, what is p? P is the x component from the vector field. Okay. And that means if we look at the change in p with respect to y, right, the partial of p with respect to y, what that's going to be is it's going to be a measure of how the x component changes as we move in the y direction. All right, so if p is the x component, then the partial of p with respect to y is going to be a measure of how that x component changes as we move in the y direction, right? The partial with respect to y is how the underlying thing changes as we move in the y direction. So, and we get to do the same thing with q. Just a second. Let's just finish writing this down. So All right, and so then the Q is the Y component from the vector field. And then the partial of Q with respect to X is going to be a measure of how the Y component changes as we move in the X direction. Okay, so that's not too difficult to understand, that we can go through and look back at the original definition. P is the X component. The partial of P with respect to Y is going to be how P, the X component, changes as we move in the Y direction. And then Q is the Y component, and so the partial of Q with respect to X is going to be how does the Y component change as we move in the X direction. All right, so knowing all that, the partial of Q with respect to X minus the partial of P with respect to Y, that should be positive, right? It should be greater than 0 when the partial of Q with respect to X is greater than 0 and the partial of P with respect to Y is less than 0. Okay, all right, so let's go through and draw ourselves a coordinate axis and think about what these two things would end up, what type of behavior we'd get if when we have this case. Okay, so let's suppose we have a point. All right, that's the point where we're going through and we're calculating the curl. Now we're just looking, by the way, we're just looking at the, this is the XY, this is an XY axis. This doesn't have Y or Z. So this is still a three-dimensional problem. You're just looking at the part of the vector field that is in the XY plane. So you can just kind of like slice through the vector field and just look at the behavior in the XY plane. Okay, so imagining, right, that we're starting at this point here, and what we're going to do is we're going to just for simplicity's sake, we're going to assume that P is equal to 0 and Q is equal to 0 at that location, right? So if P is equal to 0, then that means that the part of the vector field that points in the X direction, right? The X is the X component, that's 0. So you're starting off with a 0 vector essentially at the origin there. All right, and so so if we just kind of pick these apart individually, right? So starting with the first one here, what this is saying is it's saying that as we move in the Y direction, right? So Q is the Y component. So as we move in the X direction, the Y component, which is Q, should increase. All right, so as we move this way, the Y component should increase. What would that look like if we were to draw vectors, right? So assuming you're starting at the 0 vector, as we move in the X direction, the Y component gets longer and longer. Oop, I meant to use vectors here, but it's okay. We can just add a little vector part. Right, and it also means if this is 0 and you go in the negative direction, if it's a positive derivative, then you should have negative values. All right, so that's what the fact that the partial of Q with respect to X is positive is it telling us that at this point, as we move, as we approach that point, we start off with negative vectors that are becoming less and less negative, and then you get to 0, and then you have positive vectors that are getting longer and longer as you move in the X direction. Similarly, the fact that we have the partial of p with respect to y, this is saying that the x component is going to decrease as we move in the y direction. So the x component, that's pointing in the x direction. So we end up getting vectors that are pointing in the x direction that are becoming increasingly negative as we move away from the point. So the vectors are 0 here, and then as we move upward, as we move in the y direction, the x component should become more and more negative. That's what it means to be less than 0. So it means we're subtracting a constant from the p component. So if it's going from 0 to -1 to -2 to -3. And then similarly, if you go in the negative direction, it should do the opposite of that. And so we would get vectors that point that become increasingly positive as you go in the negative direction. So the way that you could think of this in terms of our second piece here is that you start off with a negative vector, which becomes less negative, and then eventually 0, right? Oh, no, sorry, this is a negative. So we start off with a positive vector that becomes less positive, then 0, then becomes negative. Okay, and so that gives us this type behavior, is that when we go in the x direction, our y vectors become longer. As we go in the y direction, our x vectors become more negative. Now take a look at that. What type of behavior would you get at a point if you had arrows that, if you had vectors that looked like that around it? You'd get, rotation. Okay, so when we have, this type of structure where this is, this quantity is going to be positive, this quantity represents rotation in the xy plane. Right, and so we can go back and say, oh, actually, my notes, I did one more thing for this that I thought was kind of cool. This might be helpful, maybe not. But you can also go through and sketch a similar picture for this in 3 dimensions. So again, we're assuming here that our point where we're calculating the curl is the center here. And if you were to go through and draw this picture, you could see this is what it ends up looking like. So as we move in the x direction, you're getting y vectors that are becoming longer and longer. As we move in the y direction, you get negative x and so on. Right. And so this ends up, you get this type of behavior. That's the same picture here, just drawn in 3 dimensions. So we've got our rotation and then the curl vector. So this is, again, we're ignoring the other 2 components here temporarily. So the curl vector would be the z-axis in that case. So that's what our curl vector would look like. Okay. And so looking at this, if this quantity here represents behavior that represents rotation in the xy plane, then that is going to end up giving you a, when you do have rotation, again, since the curl is the vector around which there's rotation, when there's rotation in the xy plane, you're going to have a strong k component. Okay, and so the way that you can look at that, this is just one of the 3, is that you could take this idea and you could extrapolate it to the other 2. All right, so you go through and you could extrapolate this to the other 2 portions of the curl calculation. All right, so if we take a look at it, we could say, all right, so this quantity here is going to represent rotation, for the rotation in the xz plane, and then this quantity will represent rotation in the yz plane. And so when we have strong rotation in the yz plane, we're going to have a large, the curl vector is going to be, the I component of the curl vector is going to be quite strong. And so you're going to have a curl vector that's going to point in the x direction when you have rotation in the yz. And then you're going to have a curl vector that's going to, a strong curl vector in the y direction when you have rotation in the xz. And then the ending, the curl itself is just the combination of the three. And so it becomes essentially, you could think of it like it becomes a tug of war. And then so the direction where you have the strongest rotation, perpendicular to that is going to be the strongest component. So anyway, that's the idea, is that you could go through and just kind of pick these apart one at a time. We could, as we played around with this quantity, gives us, this quantity is going to be positive and it's going to give us a strong value, a large value when you have this type of behavior. And so it does actually end up doing, what it says it is, right? So that you do end up producing a vector that is perpendicular to the rotation. So on the surface, that's crazy. You look at this curl calculation, you look at these three quantities, and on the surface, these don't look like they have anything to do with the rotation, but it turns out that each one of these calculations actually does produce a measurable value, a large value, when you have rotation that's perpendicular to the component that's really next to it, right? So this is rotation in the xy plane is the quantity for the k component. Okay, enough rambling. Let's go through and do some examples. Suppose we have a vector field that's given by x cubed yz j plus y to the fourth z to the third k. All right, and so you're asked to go through and calculate the curl of F. So we create our matrix I, j, and k, partial with respect to x, partial with respect to y, partial with respect to z. And then the I component is 0, j component is x cubed yz, and the k component is y to the fourth z to the third. All right, and so we go through we get I, and then partial of y to the fourth z to the third with respect to y. We're going to get 4 y to the third z to the third minus, and then partial of x cubed yz with respect to z, x cubed y. And then we can do minus j. So we got j, we got the partial of y to the fourth z to the third with respect to x, that's going to be 0. Minus 0, the partial of the derivative of 0 with respect to z is going to be 0. And then plus k. We have the partial with respect to x, 3x squared, yz, minus the partial of 0 with respect to y, which is going to be 0. And so we get our curl vector. So this resulting curl vector will produce the curl at any point in x, y, z. If you actually plug in the point, then you'll end up getting the vector around which there is rotation, in the vector field. All right, and let's do one more example. All right, so we've got vector field natural log of 2y plus 3zi plus natural log of x plus 3zj plus natural log of x plus 2yk. And so we can go through and do our curl calculation. Let's give ourselves plenty of space. We've got I, J, K, partial with respect to X, partial with respect to Y, partial with respect to Z, and then natural log 2y plus 3z, natural log x plus 3z, and natural log x plus 2y. All right, and so we're going to get I times, so we're going to have the partial with respect to y of our natural log function here. So the derivative of natural log, we'll use the chain rule. So we get 1 over x plus 2y times the derivative of the inside with respect to y, and the derivative with respect to y of x is 0. And the derivative of 2y with respect to y is 2. And then we got minus, so that's this, the derivative of this with respect to y, and then minus the derivative of natural log of x plus 3z with respect to z. So we're going to get 1 over x plus 3z times the derivative of the inside with respect to z. The derivative of x with respect to z is 0, and the derivative of 3z with respect to z is 3. All right, and then we get minus j. We get 1 over x plus 2y. The derivative of the inside with respect to x is 1 minus 1 over 2y plus 3z. The derivative of the inside is 3. And then plus k. And we get derivative with respect to x, 1 over x plus 3z times 1 minus the derivative with respect to y times 2. Okay, and so that's our curl vector, and I'm not gonna rewrite it this time. Okay, so that's the curl. So curl is, just to recap, the curl is an operation that we can apply to vector fields, and it produces a vector around which there is rotation in the vector field. The second quantity that we're going to look at is divergence. So the divergence is another operation we can perform on vector fields. So given a vector field, same vector field. So let's say we've got pi, qj, rk. The divergence of f equals the partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. Okay, this can also be represented as the dot product between the gradient and the vector field. So if you write that out, this is the partial with respect to xi plus the partial with respect to yj plus the partial with respect to zk dotted with pi plus qj plus rk. Okay, right, so dot products component wise, so you get this and this, so that's where the partial of p with respect to x comes from, and then this and this, that's where the partial of q with respect to y comes from, and so on. All right, so what is the divergence? The divergence is a measure of the amount of spread that's in the vector field at a point. Amount. The way that you can think about this, at least the way that I think about it, is you could imagine that you have something in the field. Usually the example I use are leaves. If we had some leaves on the field, then the divergence is a measure of how the distance between the leaves, how that how that would change over time if the vector field, if you think of it as like causing movement, right? So if the vector field is modeling fluid flow and you were at a particular point in the vector field and you think about like the flow is actually happening, are the leaves at the point, are they moving closer together in that moment? Are they moving further apart? So divergence is like, are they diverging? Are they spreading? Are the leaves spreading or are they not? So that's the way that I think about it. If you have leaves in the field, the vector field, are the leaves, sorry, do the leaves move apart? Or come together? At the point. All right, so that's what the divergence is. It gives us some measure of how the leaves are coming together or spreading apart. So if you have a positive divergence, that says that the leaves are spreading apart, and if you have a negative, then they're coming together, right? So moving apart, that's positive, and coming together, that's negative. Now, similar to the curl, at a glance, I don't think that's obvious. If you just look at the metric here, I can't think of anything with the dot product that has to do with distance. So it's not like the curl where you could try and think about, okay, well, the curl is perpendicular to rotation and cross products produce things that are perpendicular. So maybe there's something there. Instead, similar to the way that we go through and explain the curl, you can break down the divergence in the same way. Okay, so what we're going to do is we're going to do something very similar. Actually, I'm just going to focus on one of the three components, one of the three pieces of the divergence, to just kind of ask ourselves, what does the partial of P with respect to X? What does that represent? All right, so why does the divergence do what it does? And to go through and answer that question, we're going to start off with P is the X component of the vector field, right? The partial of P with respect to X is a measure of how P changes as we move in the X direction. And since P is the X component, it's a measure of how the X component changes as we go in the X direction. Okay, and so similar to the example that we did with the curl, we can, again, now we're just thinking about the X behavior here. So you don't really even need a two-dimensional coordinate axis, but let's say that we're in the vector field and we're just looking at the part of the vector that is in the XY plane. So you've just taken a slice through the vector field in the XY plane. And then on top of that, we're just gonna think about what's happening in the X direction. Okay, so we're gonna assume here that P equals 0 at the point, where you're going through and doing the calculation. And then if the partial of P with respect to X is positive, what does that end up looking like in our picture, right? So if P is 0, that means you have the 0 vector here at the origin. All right, if the partial with respect P with respect to X is greater than 0, then what that tells you is that as you move in the X direction, P should become more positive, right? And so what that's going to model is that when this happens, you should see vectors that look like this, right? So the idea being, if you're at 0 here, and you have the 0 value, so if you're at the origin and you have the 0 value for your vector field, and the change in p with respect to x is positive, then as you move in the x direction, your x component from your vector field should get longer and longer and longer. Okay. And similarly, if you went in the negative direction, you'd see the same thing. All right. So if we went in the negative direction, we'd see the same thing. And again, the way that you could think about this is that, so it's like you have a large negative. If the partial of p with respect to x is greater than 0, then if you start off with a large negative p, then p becomes less negative and less negative, then 0, then positive, then more positive, then more positive, right? And so this would model p increasing as you moved in the x direction. And again, since p is the x component, that means that the x component from your vector field increases as you move in the x direction. That models what we've got here. Okay. Now the question is, does this match up with our expectation? If you were to put some leaves, in this picture here, what are those leaves doing, at the point? Well, if you put the leaves down there, assuming that you had some movement, so they're not right on the 0 vector, you put some leaves, they're going to start moving to the right here, and as you move further to the right, because the vectors are becoming longer, they're going to move faster and faster, right? And so, as you can imagine, the leaves that are on, if you sprinkled some leaves in here, the leaves that are on the right are going to move faster than the leaves that are on the left, and so they're going to spread apart as we move to the right. So these leaves are going to become more spread apart as we move to the right here. And the same thing goes the other way, right? So if you start off with here, then as they move, the ones that are on the left side of this little sprinkled pile are going to move to the left faster than the ones that are on the right, and they are going to spread apart. Okay, so that's just one of the 3 components, but we could go through and do the same thing in the y direction and the same thing in the z direction. And what the divergence is the sum of the spreads that are in each of the coordinate directions. And you can also look at this the opposite way too. I did go through and just kind of jot this down. So if we had a negative value, what does that end up doing for our picture? So if we go through, and again, we start off and we have p is 0 here at the origin, then what happens with a negative value is that you should have a larger and larger negative p component, right, to your vector field as you move in the x direction. So that just means that you should have arrows that are pointing faster, larger and larger arrows are pointing to the left as you move in the x direction. So we should see something, a short arrow, and then I don't know why I didn't put that on the axis. A short arrow, a longer arrow, and a yet longer arrow, and then the opposite on the other side. You can kind of tell just by looking at what type of behavior you'd see here. The arrows are all pointing toward the origin. So you can imagine if you had some leaves that they're kind of pressing inward. But you could use the same kind of analysis that we did here, right? So if you were to go through and just sprinkle some leaves at some spot on here, right? And so those leaves are spread over, a short distance. The ones that are on the left side here that are closer to this arrow are moving slower than the ones that are on the right side that are closer to this arrow. And so the leaves are being pushed together. And so you get, a tighter, more compact set of leaves as if you think of time passing and the vector field to be modeling flow, it's going to push those leaves, closer and closer together, right? And so this idea here of going through and just taking the first component from your divergence and just thinking about what that models, we can see that when we do have a positive value for this for this calculation, we do end up getting spreading behavior in the vector field. And when we have a negative value, we do end up getting compression behavior. And again, the divergence is just the combination of the three. So you go through and you figure out how are we spreading in the x direction, how are we spreading in the y direction, how are we spreading in the z direction, and then combine them to get how we're spreading for the vector field at the point. Okay, so that explains why the divergence, why it does what it says it does, and why it works. So if we have f of x, y, z, and let's go through and say that we've got x cubed, y, z, j. So we're using the same vectors we used earlier. Y to the fourth, z to the third, k. All right, so if we're going to do the divergence of f, it's pretty straightforward. You're going to differentiate the x component with respect to x. So there is no x component here. So the derivative of 0 with respect to 0 is going to be just 0. And then we're going to differentiate this with respect to y and this with respect to z. So the derivative of this with respect to y, we're going to get x cubed z. The derivative of this with respect to z, we're going to get 3y to the fourth z squared. Okay, so divergence, no vectors here when you're done. Divergence is not a vector. The result is just a quantity. So this quantity here is going to give us a measure of what type of spread we would have in the vector field at that point. We just take the point, plug it into this, and that will tell you what type of behavior we have in the vector field at that point when it comes to spreading behavior. All right, we can also do the other problem we did earlier. So x, y, z, we had natural log of 2y plus 3z plus I plus natural log of x plus 3z j plus natural log x plus 2y. Okay, and so we can go through and do divergence of f. So we're going to differentiate this with respect to x, this with respect to y, this with respect to z. And if you notice, there's no x's here. So the derivative of the natural log of 2y plus 3z with respect to x is 0. The derivative of x plus 3z with respect to y is going to be 0. And the derivative of natural log of x plus 2y with respect to z is also going to be 0. And so we get 0 from our divergence calculation. Okay. And so that gives us, so that's the video on curl and divergence. So just two different calculations that you can go through and apply to vector fields. The first one, you go through and when you calculate the curl, so just a couple things to be very clear about. The curl calculation produces a vector. So that's very important to remember that the curl produces a vector, and it's the vector around which there's rotation at that point. And then the divergence produces a scalar quantity, and that scalar quantity is a measure of the amount of spread in the vector field. So curl produces a vector, divergence produces a scalar. So those are two things that are important that sometimes students lose track of. And the calculations themselves are pretty straightforward. And so that's the video. All right, thank you for watching. See you next time.